All right. Well, thank you everyone for coming down. My name is Justin, and I am going to be talking about the CANBUS, specifically CANBUS in automotive applications. So a little bit about me. My name is obviously Justin. I go by JDog Herman on Twitter. You can also find me on Keybase. I'm an active board member of the Northeast Ohio Information Security Forum, which is a group that's been going on for about 12 years, I think, maybe more, in the Cleveland region. And if you guys are ever in the area and you're looking to sit in one of our meetings, just reach out to me. I'm a penetration tester in the finance industry. I'm into electronics and ham radio, and also a big board game geek. So if you ever want to talk to me late at night, you talk to me about those things and I'll talk forever. So you have been warned. I am not an expert in this. I don't claim to be. I don't pretend to be. I'm not responsible for any of the troubles or anything you do to your cars or anyone else's cars or a rental of cars or anything else. I'm not, don't follow what I'm saying. The opinions are my own and not of my employer. Last year, I drove a pretty non-remarkable car. It's a 1996. I don't know if you guys are familiar with the Ford Aspire. It's this very small hatchback, looks like a shoe and drives down the road. It has nothing fun in it to be able to really get advanced information from. You got basic ODB2, hardly any other information you can really draw from that. So last year, I got myself a newer car, this time a little bit older, but it meant that I could have a new toy and I could go ahead and take things apart and figure out how far I can go with this car hacking thing that was available. So when I began, I was looking for obviously the vector to get into the system, and that's of course the ODB2 port, right? Everybody uses those. In Ohio, we plug in, you get emissions testing that to say if your check engine light's on, you don't pass, and so on and so forth. I didn't know much about the connector itself. So what I found in my research was that the SAE defined the connector as a J1692. It has 16 pins. It's sometimes called the data link connector, and by specifications, it's supposed to be no more than 2 feet from the steering wheel and not supposed to be require any tools to access. Now, my car specifically leverages some other pins, but the standardized connections are to use the 1850 with SAE for both pin 2 and pin 10, ground on 4 and 5, both for chassis and signal, along with ISO 15765-4, CAN bus high on 6. Pin 14 has the ISO 15765-4 for the low, and then of course both the K line and L line and a 12-volt power supply. I didn't know what any of this meant, and so I started trying to look in to find more information, and what I found was that the SAE J1850, which is on pin 2 and pin 10, those are really designed for the Fords. They used pulse width modulation to control it, while GMs leveraged a variable pulse width. The ISO 9141-2 is for Chrysler, European, and Asian cars, and the ISO 14230 for K-line and L-line were for other types of vehicles that weren't included there. One cool point that I found about this is that not all of these connectors are the same. There's actually a second specification that's out there which permits for 24-volt applications, and in that case, there's actually a divider in the middle, which doesn't allow the insertion of the male plug. So OBD2 was required by CARB, which is the California Air Resources Board, back in 1991, and that's really was pushed by for emissions testing. They were having obviously bad emission issues in 1970s, 1980s, and California is always trying to lead and champion that. And so in 1991, they required some sort of onboard diagnostics. In the US, all cars built after 1996 had to have ODB2, and it was primarily used for diagnostic support information regarding, again, just emissions. And At this point, I got a little confused trying to understand what ODB2 was versus CAN. I've heard both of these together, and what I found was that the ODB2 is basically just sits on top of the CAN bus. It's a language, as you could maybe say, that would be able to communicate in certain standardized parameters. CAN, which was the 15765-4, was required after 2008 for all cars. So if you're thinking about doing this, getting into hacking on cars or having some fun and figuring out what's out there and doing some fuzzing, having a newer car obviously is going to offer a lot more features. So what happened to ODB1? Well, ODB1 didn't actually exist. That was manufacturer specific to whatever their whims were. I've had a vehicle that actually required me to put a jumper, a piece of wire over a port that looked like an ODB2 connector, as they say, and instead the check engine light would flash in certain sequences, and that would tell you your error code that was available. Again, usually those were, again, for just emissions testing. So the CANBUS was actually designed by Bosch in the 1980s, and in 1991, they released both a CAN 2.0A and a CAN 2.0B. This was adopted in 1993 by the ISO 11898, the ISO standard. Now, the difference between A and B is actually the address length. In A, you get 11 bits of data for addressing, and in B, you get 29 bits of addressing. When you think about like the OSI model, the CAN bus sits basically in the data link and physical layer, while ODB2 would be more transport and network. So the three different standards that were established out. There's 11898-2 for high speed. This was a binary 1 which is considered dominant. Binary 0, which is considered dominant. It's when it's driven low for low signal, and then driven high, where high signal. Binary 1 was recessive, and it commonly floated at around 2.5 volts. And then when it would return back, they both return to the 2.5. In ISO 11898-3, there was a low speed signaling, and I'll show you a little more about that signal and how that one works. And then ISO 15765-4 is the one we're really going to be talking about, and that is a form of the 11898-2. This shit's complicated. So CAN bus high speed, again, this is that high speed I was talking about. There's a differential between both the high voltage and low voltage, and both signals, the high and low, are driven to their respective voltage potentials. It signifies a 0, and then when in return, they signify a 1. And that's how this high speed ISO standard was established. This is, again, the one we're using. High-speed network was all on a standardized bus system. They had a stub length of no more, and the standard is no more than 30 centimeters. Linear bus is terminated at both ends with 120 ohm resistors, and everything needed to be basically in a line and connected up. They did come out with, again, the low-speed option, which allowed the individual nodes to terminate and actually bring up their resistance, both ground and their 5 volts. But the total resistance on that was around 100 ohms, and with no more than each node having at least 5 ohms of resistance. The speed for the high speed is 500K, and I think it said the total length could be about 40 meters. With the low speed, you're talking about 30 to 125 kbits. So in low speed, you were driving individualized signals which are closer to 5 and closer to 0, and inversing them. Now that time for that collapse of the signal is the reason why we have to slow down the transmit data transfer that can actually occur. Low speed can work in a star or mesh topology. It's far more flexible, but again, you've got that low speed. And when you are talking about certain systems in your car, high speed is going to be necessary for like your engine control and transmission and brakes and so on and so forth. While the low speed systems can be the seat heaters and the instrument cluster and radio, more creature comforts in the cabin. So there's 4 types of frames that exist on the CANBUS network. There are data, for sending obviously data, the remote, which is to request data, errors, and overloads. And errors and overloads are basically sisters of one another. When you have an error, the system, if it detects one during a frame session, it will go ahead and transmit 6 dominants, which is our zeros, followed by 8 recessive ones, and then followed by the interframe spacing of at least 3 dominants. If the system detects needs more time for processing, it will create an overload, which is the exact same signal as the error, but not in between a data frame or remote frame. If each node, as they're working on the system, will actually keep a tally of how many errors that they're occurring. And if they see less than 128, they will go ahead and send an active error frame. If their transmit or receives more than 250, they'll put a passive frame, which means they actually don't transmit. They just sit for the allotted time. And if the transmit is greater than 255, the device just stops participating altogether in the network until it's reset for most types of nodes. So the data frame starts out with obviously starter frame. It marks the beginning of the data and the remote signals. I'm not sure if you can see this, how well it is, but that's the portion in just a little white. The green is arbitration field, and this includes the message ID and the remote transmission request bit, which that determines whether or not this frame is a remote request or a standard data frame. Also the identifier is in that arbitration field. That can be, again, the 11 bits, or it can go to 29. The next is a control field, which is just reserved, and used to determine, there's a reserved bit, and then there is a control field, and it's used to determine the data size and the message ID length. So in a frame, if you want to send additional data beyond the payload that's allotted in its data field, you would send a 1 in that control field, versus you sending a 0, which is a single frame. Each subsequent frame would get a 2 instead of a 1, and flow control frames, which help determine the speed and accuracy, those are 3, and then 4 through 15 are reserved. Data field, this is actually where the data goes, and really only applies to data frames and not remote frames. CRC field is a checksum that's available to help to determine that the message was not garbled when it was received. And then you'll have an acknowledgement along with a delimiter and then an end of frame. All CANBUS 2.A will have this exact same thing. Now, if you want to get to 2.0B, what you're going to do is you're going to change out the arbitration field and make that a 1 instead of a 0, and then that will actually extend the total amount of data that you can total send, but you're going to then, just after that remote, the arbitration field, you'll have another section, which will be another 19 bytes, allow you to have additional identification. So when 2 nodes on the network identify a collision, or as they're processing through, they need to arbitrate who's going to actually transmit. They will listen for their own transmission, and then after they have waited the allotment of time, they will go ahead and process based on their message ID. Lower message IDs receive a higher priority. ODB2 lives on the CAN bus, and it's a part of the Unified Diagnostic Service. That is closed source, and Ford has been generating some OpenXC, which is another type of replacement for the unified diagnostic service, but I don't have enough information about that. OBD2 messages are again filled out. This you can see it on the request 7DF0201. The 7DF is the identifier along with the bytes and length, which is 02, and the mode that you're requesting. There's a series of modes that are in OBD2 messages. When DTCs come up, or diagnostic trouble codes, they are appended with a P or B or C or a U. That stands for powertrain, body, chassis, or user. The second digit determines whether or not it's government issued or a manufactured issue. And then the third digit will determine the system that it's actually involved in, with subsequent being the actual error message. So if you're getting started, and I know this is going to run a little bit long, I began with using an Elm 329 and Torque. It's basically Android app. It's available for free. And that's the Elms 327 are pretty good for just checking ODB2 messages. But I wanted to get into something a little bit more, and I wanted to actually send CAN messages. So I actually picked up a scan tool, an OBD2 Link MX Plus. Didn't really offer me enough control, and I found that the buffers were overflowing, so I went to a Machina M2 Open Loop and comma AI Pandas in order to enumerate the CAN network. I'm aware that there's CAN-TAC, CAN-DO, and CAN-ABLE. I've not used any sort of I don't have any experience with those. The software that you're going to use for that is, at least I used, was SavvyCAN and PuTTY with or Hyperterminal. But if you're in a Linux environment, SocketCAN is a great option along with CANutils. And if you have Wireshark on a Linux machine, you can actually address CAN messages that way. So when you're collecting data, you're going to reduce the signal to noise. So what that meant for me was I turned the car off and captured a baseline signal when the system was still initialized. So just after turning the car off, waiting, captured that particular baseline, and then went and captured a known signal. So 5 presses of a key, or pushing the pedal down and back up with a known sequence. From there, I take both data sets, and I will go ahead and eliminate the baseline from the sample, and basically rinse and repeat. Do this multiple times in iterative, and then I've got something to really work with as far as analyzing. So I would then count the incidence of messages from the filtered sample data, and then I look for timing between the messages. So if I push the pedal 5 times and I only see one action, then obviously the count is not correct. If I see 1 at the beginning and 3 at the end, and I push it 4 times, then it's probably an issue because I should have been coming up in even patterns. And I'll eliminate matching signals between, so if I'm pushing a button on the steering wheel for up, down is probably going to be fairly close in coming from the same module, and might be similar data, so I can use those. When you're testing, obviously there could be dragons there. That's concerned because you're now transmitting onto the bus, and you don't necessarily know what every message that you're sending out. But hopefully whittling that down using some frequency analysis is a strong way to be able to get yourself in a better position. I did have my car lock up where I needed to power cycle it, but a simple power cycle fixed that. Division testing is another method for determining which messages are what and trying to reverse engineer those. So you take the full sample, you retransmit the first half, and you see if the impact on the system is viewed or not. If it was, then you divide that first sample up. And of course, 3 is fuzzing. It's not very effective because there's a lot of data points that can happen in there, and it becomes very difficult. Once you've got the message, or you've got an idea of the message, and you want to know more about what each data bit stands for, there's an OpenDBC, which is basically a lookup table between how to convert the data sections in the message to human readable information. So, how many RPMs and such. Some suggestions if you're looking to try to do To do this is obviously look for pattern recognitions, and I recommend Google search. Searching for similar makes and models and brands is a strong way that you'll find more information. Some ideas, if you're looking to get into yourself, would be preconditioning your car, or autopilot with AI, home automation, so when your car gets home, because it has a GPS most likely, that you can go ahead and receive that, make other automations inside your home turn on or whatnot. And AV controls, if you're like mine, I have my phone set up so when I connect to the audio jack instead of Bluetooth, I can still use the thumb pads, directional keys on the wheel in order to control the phone. Additional resources, obviously the Car Hacking Village is a great opportunity. Building your own bench lab is very informative. Car Hacker's Handbook, excellent book, available by No Starch Press. And found out this today is actually there is an application called IC Sim along with CAN utilities, and you can actually create a virtualized bus in order to attempt to learn a little bit more and experience yourself. And with that, I'm all finished. Thank you.